So in this video we're going to be talking about how to use polar coordinates to solve double integrals that may be done on regions that have some circular properties to them. So let's consider, first of all, let's draw the xy plane. Let's draw the xy plane, and now let's have some semicircle, well, not semicircle, just a quadrant of a circle, and that's going to be our new region of integration. So remember, when we integrate a function of two variables, we need to define a region of integration on the xy plane. So essentially, trying to perform integration on a region like this would be certainly quite complicated, because we know even though x is the independent variable, so it would have finite limits. Let's say this is the unit circle. So let's say that that's a unit circle, that's the first quadrant, and obviously x is going to go from 0 to 1. And then y is going to be modeled by this function. So y is going to have to be square root of 1 minus x squared. And basically it is going to go from 0 to that function. Now obviously the first thing we notice is that depending on the function f of x, y that we have, the double integral, once we integrate for y first, we're going to get an expression for 1 minus x squared. And if it so happens that the new function that we're integrating with respect to x does not have anything that allows us to use our standard methods, such as substitution or integration by parts, then it would be impossible to get an analytical solution for a problem. So what we can do instead is we can transform the domain of integration, so we can transform coordinate systems so as to change the limits of integration to something that would be a lot more practical. So here's where polar coordinates come into the picture. So basically we're going to define these two new variables. The first one is going to be called r, so that's the radius of that circular area or region. And then we're going to have the angle from the x-axis, so that's going to be called theta. And the parameterization we're going to use is basically for any point that we have on that circumference, on that unit circle here, we're going to have the following. What is going to be the horizontal length of that? Because if we draw a triangle like this, r is going to be the hypotenuse, so and theta is going to be the angle. So we can relate x to r and theta by saying r is equals to cos theta. And hopefully that's a very intuitive thing for you to see, since you should be really good with trigonometry by now. And obviously y has to be r sine theta. So that's the parameterization we're going to use. And obviously we know that by definition we should have the relationship x squared plus y squared equals to r squared. Now, how do we go about deriving? Because remember, when we're performing a double integral on a region D, let's call this region D, and let's say we have something like, well, some generic function of x and y, really, dA. Our element of dA is usually dx dy, but obviously that's not going to make it. That's not going to allow us to find it. So we need to find an equivalent form in polar coordinates. So the first thing that comes to mind is to use dr d theta. But obviously it shouldn't be like that, because remember, we're not transforming from the same domain to the same domain. So there needs to be some scaling factor involved to complete that transformation. The transformation is not going to be one-to-one, obviously. So there needs to be another element added to this element of area in polar coordinates. So how do we find that? There are two ways. I already talked about how we can use the Jacobian, or the determinant of the Jacobian, for the transformation from xy to r theta. So we defined it as this, and if you remember from that video where we introduced the Jacobian for the first time, we talked about how this would be a 2×2 determinant of the partial derivative of x with respect to r, then x with respect to theta, then y with respect to r, and then y with respect to theta. So basically by putting in these two values here, taking the partial derivatives of those, we got the following Jacobian, which was just r. So that means that the element that we're going to put in here is going to be r. And that all made sense. So this is the proper formal way of transforming from one coordinate system to the next and finding that scaling factor that is going to be part of our area element or even volume element. In the case of a triple integral, this is the same thing, but we're gonna be using a 3x3 Jacobian to find the scaling factor for a volume element in the transformation of coordinates. And we will go through that in some videos after we talk about triple integrals. But for now, let's focus on this. There's another way that is a little bit more intuitive and allows us to visualize what is actually happening. So I'm going to define x and y. But now what I'm going to do is I'm going to have two arcs. And what I'm going to do is I'm going to take a little slice of that. So you can imagine that this is going to be some little slice of that two arcs. And this area, I'm going to call it an infinitesimal area, dA. So that's going to be my dA. So let's say that these two arcs are pertain to circles that are centered at the origin. So we know that this distance is going to be the radius r itself. That's the maximum radius we're going to have. And then that means that because this is an infinitesimal element, this little length here should be the r. Now the next one obviously needs to be this one. You would be tempted to think, well, if this angle here is d theta, right, because it's an infinitesimal angle, then that means that this should be d theta, right? But remember, d theta is just an angle, it's not a measure of length. So to find the length here, we need to use the fact that this is going to be the arc length. This little length here is going to be the arc length. And as you remember from basic pre-calculus, the arc length is going to be given by L times theta. So L is just the length there. Sorry, the radius. That should be the radius, right? It's the radius times theta. So theta, assuming that it's quite small, or whatever expression we want to express in terms of radians. So in this case, since our angle is d theta, this is going to be equal to r d theta, because the total radius, the total distance from the center to that particular arc is going to be the radius. So now that we have that, because it's an infinitesimal element, we can treat it sort of like a rectangle because the limit is small enough, which means that this is just going to be this length times that length. So that means that dA is going to be r dr d theta. And we usually try to put these two together one after the other just for convenience of integration. So this is another way in which you can derive that relationship that I just talked about. So this is all really good, but how do we actually apply to solving a problem? So let's go through a simple problem. Let's start with a simple problem just to give you an intuition of what this method looks like and how it works. So I'm going to draw the xy plane once again, and I'm going to have the following region of integration. So it's going to be an annulus, and an annulus is essentially just two circles, concentric circles, and basically the region is going to be the area between them in this first quadrant. So this is going to be a region D. So these are going to be the coordinates. So basically this little circle is going to have radius 1, and this outer circle is going to have radius 2. And the idea is to find the following integral. So we're going to have double integral of the function x plus y dx dy. So we will evaluate this, but we'll do it by using polar coordinates. Since we have this circular kind of region here, it's more convenient to use polar coordinates. So the first thing we need to do is establish new limits. So for theta, what we're going to do is we're going to start from here. So the function starts at the x-axis here from 0. And how long does it travel? How long does the angle travel with respect to the xy plane? Well, it goes, it basically takes up a full quadrant, which means that the limit here is going to be pi on 2 because it completes 90 degrees of a rotation here in this region. So that's going to be our limits for theta. And then for r, what we're going to do is we're going to grab a radius, and then we're going to see what are the limits for the radius. What's the minimum value of the radius within this region? Well, since we have two concentric circles, this is going to be a constant value of r, so that's going to be 1. and then the outer one is going to be a constant value of 2 because the radius is not really changing. It just follows that perfect circular arc. So that's going to be the limits for r. So now we're going to establish the integral, which is going to look like this. So usually we write d theta outside. So we're going to have pi on 2, 1 to 2, and now we're going to have the following r cos theta. So remember, we need to make the substitution into this formula, and we define x as r cos theta and y as r sin theta. And now we're going to multiply this by the element of area for polar coordinates, which we just say is r dr d theta. And be very careful, because a lot of people forget this little scaling factor here, because it needs to be put in here, otherwise you get a completely wrong answer. So don't forget to put that little r there. So that's going to be our integration. So now what we can do is we can expand this to group the terms together. So we're going to have the following. We're going to have r squared cosine theta plus sine theta. So this is going to be dr d theta, integrate with respect to r first. So this is going to give us, I'm actually going to do it here, 1 over 3. So that's going to result from integrating r. I'm going to put it outside as a constant. So r cubed times cosine theta plus sine theta. And then we're going to go from 1 to 2. And now what we're going to do is we're going to basically put those values in. So this is going to be 9 minus 1. So that's going to give us, the following value. Oh, don't forget the d theta element here. So we're going to integrate with respect to d theta next. Yeah, so we're going to get the following. 1 over 3. 2 cubed, that's going to be 8, minus 1, so that's going to be 7. So let's move that 7 outside the integral. 0 pi on 2 cos theta plus sine theta d theta. Now we integrate this, so we're going to get the following. Sine theta minus cos theta, 0 to pi on 2. And then here we're going to have 14 on 3. So that's going to be our final result once we plug those values in. And you can see that we perform a really nice simplification here, because when we integrate with respect to r, all we needed to do was use this little power change here. But that was all we needed to do. So it was a fairly simple double integral. If we had tried to use Cartesian coordinates, remember the limits for y would actually have been 2 semicircles, which means that the limits for y would probably have looked something like this: 1 minus x squared, and then 2 minus x squared. And that's just a horrible expression to have, because once you integrate, once you replace those limits into your outer integral, that's going to be fairly complicated to integrate. So obviously, by using polar coordinates, we simplified the problem. And in the next video, we're going to continue doing some more examples just to give you an idea of how this whole process works.